Good morning from Colorado, and welcome to ISART 2020. My name is Rebecca Dorch. I serve as the Senior Spectrum Policy Analyst at the Institute for Telecommunication Sciences, ITS, the research laboratory for the National Telecommunications and Information Administration, NTIA. I've been involved with this NTIA program, the International Symposium on Advanced Radio Technologies, ISART, since I joined ITS in 2016. As is a tradition with ISART, we open with a tutorial. The topic ISART is tackling this year, 5G spectrum and a zero trust network, involves a tremendous amount of cross-disciplinary understanding. So to help set a baseline of common understanding for those joining us from different disciplines, areas of expertise, and levels of knowledge, we asked our tutorial panelists to do the impossible. Explain what 5G is from an engineering, architecture, standards, spectrum, and international perspective in under 2 hours. And then to record those presentations so that registrants could view them in advance. On behalf of NTIA and our ISART co-host, the National Institute for Standards and Technology in the University of Colorado at Boulder, I want to express my sincere appreciation for the outstanding presentations we are about to see. They each did a phenomenal job providing the baseline we sought. I will briefly introduce each of our 5 distinguished and accomplished speakers prior to showing their presentations. And additional information about all of the speakers is in the ISART program and the ISART app. At the conclusion of the 4 presentations, we will all be here live and in person, virtually of course. And please feel free to ask questions online during the presentations and to vote for questions that you too would like to have answered during the Q&A portion of the tutorial. Now, remember, of course, that our panelists from government agencies are speaking based upon their knowledge and expertise and not on behalf of their respective agencies. So, first up, we'll learn about engineering and architecture underlying 5G from Professor Jeff Reed and Professor Nishith Tripathi. Professor Reed is a founder of Wireless at Virginia Tech and has a distinguished career teaching, advising, and directing programs and initiatives and establishing companies related to wireless security and technology. Professor Nishith Tripathi is an adjunct faculty member at Virginia Tech and a research and development strategist at Samsung Research Research America. He and Professor Reed co-authored a multimedia book on 5G, which explains the vast potential of 5G and key 5G concepts in about 55 hours, and I've asked them to cover it in about 20 minutes each. So we're grateful to both of them for sharing their knowledge with us. So now, without further ado, we will see the very first video, 5G Fundamentals and Deployment Considerations.
Hello and welcome to our tutorial, 5G Fundamentals and Deployment Considerations. My name is Professor Jeff Reed, and my colleague, Professor Nishith Tripathi, will be presenting this tutorial. It's based upon our ebook, 5G Cellular Communications, Journey and Destination, and you can find it at the link below. First, let me tell you a few things about myself. I'm the Willis G. Worcester Professor of Electrical and Computer Engineering at Virginia Tech. I have founded a number of different organizations, such as Wireless at Virginia Tech, the Ted and Karen Hume Center for National Security and Technology, several companies, Cognitive Radio Technologies, Federated Wireless, and PFP Cybersecurity. I've also co-authored several books, most of those books with Professor Tripathi. I'm also a winner of the International Achievement Award by the Wireless Innovations Forum.
Hello, I am Nishith. I work for Samsung and Virginia Tech. With Dr. Reed, I have co-authored a couple of books, including the first multimedia book on 5G and a textbook on cellular communications. I have contributed to organizations such as the FCC, GSMA, Scientific American, and CTIA.
Let's talk about the goals of this tutorial. First, we're going to provide examples services that 5G was targeted to support. Next, we will look at the performance goals for 5G in terms of data rates and latency, and we'll look at the construction of the overall system architecture. There's some very important features of the architecture, including network slicing, a service-based architecture, and multi-edge computing. We'll summarize the key characteristics of new radio air interface. This is the air link between the handset and the base station. And we're going to talk about two important features of the architecture, standalone and non-standalone modes for 5G. And this is important, particularly as we discuss the spectrum aspects of 5G. So our first topic, let's talk about 5G fundamentals, the services that are targeted by 5G and their respective performance goals. To give some context to 5G, and let's take a look at the evolution of 5G. It seems like every 10 years we have a new wireless standard. These standards come from the 3GPP organization. 4G was defined in 2008, and 5G began its definition in 2018 with the release 15. Phase 2 of 5G is release 16, and that's expected to occur in July of 2020. So what can 5G do for us? Oftentimes you'll see 5G represented by this triangle, in which we have three pivotal services: enhanced mobile broadband, ultra-reliable and low latency communications, and massive machine type communications. These services allow for various applications. For instance, with enhanced mobile broadband, we see gigabytes in a second. And with ultra-reliable low latency, we see applications such as self-driving cars, and massive machine type communications is there to support smart cities. We'll be seeing the combination of these services supporting other applications, such as enhanced 3D videos, or augmented reality, or industrial automation. Combinations of properties of massive machine type communications and ultra reliable low latency are useful for mission critical applications. And then finally, the combination of enhanced mobile broadband with massive machine type communications is very useful for smart home and building applications. Let's take a look at the performance of 4G versus 5G. IMT 2020 specified the recommendations for 5G, while IMT Advanced specified the recommendations for 4G. And as you can see from this diagram, 5G provides much more performance than 4G systems in many critical areas. Peak data rates of up to 20 gigabits per second, user experience data rates of 10 times the previous ones, spectral efficiencies at 3 times, user mobility, much faster speeds to support things such as high-speed trains, very low latency. And this, I think, is perhaps one of the most important of the properties of 5G, this low latency, because it opens up a variety of new applications. Connection densities, an incredible amount of 100,000 devices in a square kilometer, energy efficiency of 10 times the previous, and finally the overall capacity 100 times greater with 5G versus 4G. So how do we build 5G? Well, it's composed of a number of new components, such as new radio, new network architectures, virtualization technologies, new devices, and new applications that are supported by 5G.
Let's start with the system architecture. We should get ourselves familiar with some definitions. The user equipment, UE, communicates with the access network, which could be 5G access network, so-called next generation radio access network, or a non-3GPP access network. Then we have 5GC or 5G core network, also called next generation core. NGC interfaces with the outside world, some data networks such as the internet. When we combine the UE, 5G access network, 5G core network, what do we get? A 5G system. A network function, NF, is some 3GPP defined or 3GPP adopted processing function in the network. For example, the base station GNB is a network function.
Let's talk about the major features in the 5G network. First, we have NGRAN, the next generation radio access network that allows LTE and 5G new radio to work together. Then there's the Cloud RAN aspects of 5G. The radio access network can reside in the cloud. 5G has a new core network, 5GC. Sometimes it goes by other names as well. That 5G core is a service-based architecture in which the components of the core network can reside at different locations within the cloud. There's a number of different radio access network architectures, combination of 5G base stations, 4G base stations, 5G cores, 4G core. The multiple access edge computing network, or MEC, allows for applications to reside near the edge of the network. This is one of the neat features of 5G that allows for very low latency. And finally, perhaps one of the most significant aspects of 5G is that it was developed with network slicing in mind. So you can share a physical network, but the networks can be separated under different slices. Each one of those slices provision for a different quality of service experience, or different authentication, or different security.
The next generation radio access network is NGRAN. So what do we have in the NGRAN? So we have 5G base stations, GNBs, next generation node B. So the GNB communicates with the user equipment through the new radio or NR air interface. Also, we can have some LTE base stations that have been upgraded to understand the 5G core network. So we call them NG, next generation ENB. So these ENBs talk to the UE using the LTE air interface. Now, the standard allows the GNB to be decomposed or disaggregated into two components: central unit CU, distributed unit DU. So central unit allows pooling of resources, and distributed unit is closer to the cell site. So it has the RF equipment. Now, what are the key benefits we can get from NGRAN? Well, we can benefit from high performance 5G NR air interface. We get quite a bit of flexibility in deployment, and we get cost savings when we do such disaggregation of the GNB. core. So we have a variety of network functions in the 5G. Here we'll take a look at some of those. We have access and mobility management function that exchanges non-access stratum NAS signaling with user equipment. For example, messages related to authentication. We have session management function that allocates an IP address to the UE. UPF, user plane function, is a gateway to the outside world. So the packets from the outside world, a web server will pass through the internet routers, will arrive at the UPF, UPF to the GNB, and GNB to the UE. The important aspect is that we have modularization. So we have more than a dozen different network functions. This architecture gives us benefits such as scalability, flexibility of supporting network slicing, a variety of services, some we may not even know today, and it gives us cost savings. One of the key features of the 5G is SBA, service-based architecture. So each network function provides a set of services. For example, AMF says that, okay, I provide certain services. It will let the network repository function about that. And session management function will also contact NRF. So now NRF knows that we have this AMF alive, this SMF alive. So if somebody is looking for an AMF, they can talk to the NRF. These kind of network functions can store data in some storage functions such as UDR and UDSF. So they can store information as well as retrieve information. For example, information about the subscriber. What are the benefits we get from SBA? Well, it facilitates implementation. There is increased resilience because you can have the data separated from the computing resource. So if we lose computing resources, we still have the data intact. We can start another processor as the AMF. Another aspect of 5G is MAC, multi-access edge computing or edge computing. So the idea is to bring the processing closer to where the users are. So if we look at traditional processing, then the user traffic will go from application server through the internet routers, core network, radio network, and to the UE. So this core network highly centralized. Now, when we go to MAC processing, we bring the application close to the user. So the packet from the application server will arrive at the mobile edge host, and then we place some gateway like UPF we talked about, user plane function, and from that gateway to the radio network, our GNB, and GNB to the UE. So we are not passing through a big comprehensive core network. So that will give us several benefits. For example, we will be able to reduce the latency because now the server is close to the user. There will be less traffic in the backhaul and core networks, and we can make use of some things we couldn't do earlier. For example, location aware and RAN aware services, because this application server is closer to the radio network and it can talk to the the radio network and exchange some information. Network slicing, another very important feature in 5G. So the basic idea is to provide custom quality of service for a variety of services as well as customers. So we create different logical networks by using the same physical infrastructure. So for example, in the standard, we have enhanced mobile broadband slice. So that has data rates with much more importance. So we provide high data rates to the user. Then we have ultra reliable low latency communication slice. So here latency is very, very important. Then we have yet another slice, massive machine type communication. Here our coverage is very important. Maybe there is a vending machine in the basement of a building, so coverage is important. So basically we have different slices to take care of different types of services. So we get several benefits like custom quality of service and cost savings. So we use only those functions that are required. We can rapidly deploy services because we have done the customization.
Now let's take a look at the fundamentals of the new radio error interface. Let's take a look at creating the new radio error interface. First of all, 5G was developed with the ability to support a variety of spectrum, shared, licensed, or unlicensed spectrum. It has the capability of supporting massive Mimo, particularly at higher frequencies, to improve the throughput and range of the system. It has a very flexible framing structure. One thing you have to say about 5G is that it's the ultimate in flexibility. It means that actually a lot of flexibility in the formation of the OFDM signal as well, such as spacing of the subcarriers. There are advanced coding techniques that are incorporated in the error interface, and the ability to connect to multiple radio access systems. Massive MIMO is one of the key features of the 5G physical layer. You can have hundreds of antenna elements at the base station to enhance the overall performance. These antennas, when combined appropriately, provide for high gain and narrow beams. They can be used to support multiple users by pointing to different users in space to separate those users and increase the overall capacity of the network. Or you can use spatial multiplexing in order to improve the overall throughput rate by using different propagation paths to convey the information. So you get high throughput and high capacity using MIMO antennas.
5G has quite a flexible frame structure. So we have a self-contained slot where the resource allocation, data transmission, and even positive or negative acknowledgement can all occur in the same slot. Now, the slot itself is of variable length, so we can have longer slot or a shorter one, and that will help us adapt to the quality of service requirements. We not only have backward compatibility but forward compatibility as well. So we have traditional 1 millisecond subframe in LTE. In 5G, that subframe has one or more slots. So some slot could be used in future to define a new kind of air interface. We have quite flexible OFDM numerologies. What is a numerology? It is basically a configuration with a certain subcarrier spacing. So for example, if you look at LTE, we have 15 kilohertz spacing for a typical channel. So between two subcarriers, rock solid fixed 15 kilohertz. But now in 5G, it could be 15 times to 30, could be 60, 120, and so on. So we have more options in 5G. So that allows us to have a low complexity processor, even though we might have large channel bandwidths. It helps us meet quality of service requirements, and it facilitates diverse deployments. So we can have low band, high band, and still have reasonable processing complexity. Channel coding is quite advanced in 5G. So for example, traditionally in LTE, when we want to convey resource allocation, for that signaling we use convolutional coding. But in 5G, we use polar coding. So that will give us benefits like better error protection, more efficient to decode. When we talk about data transmission, in LTE, we use a turbo coding. But now we have low density parity check coding. So that has the benefits such as higher throughput, the complexity is relatively lower, and we save some power. Okay, time to talk about some 5G deployment considerations. So Dr. Reed, let's start with network architectures.
5G has a number of candidate architectures, combinations of base stations and core networks. The most popular eventually will be option 2. We call it the standalone option, with new radio mixed with the next generation core. Option 3 is what we're seeing deployed today, primarily the non-standalone option, in which we take new radio and we use the old core network with it. But there are various options, some with different types of base stations mixed with next generation cores or with the old 4G core. And of course there's option 1, Utron with an EPC. The most common option will be the standalone architecture, option 2, that consists of the new radio connected with the next generation core network. That next generation core network will connect to the 5G base station, the G node B, both with the user plane and the control plane. And of course, the information will be relayed from the next generation core through the 5G base station, the G node B, to the user equipment. It is this architecture that allows us to realize the full potential of 5G. However, it requires a new core network as well as a new radio network. Hence, this is more of the later deployments of 5G.
Option 3x, quite popular, also called non-standalone NR with EPC or ENDC, EU Trainer Dual Connectivity. So basically our UE can have connectivity with both LTE ENB and 5G GNB. So one of the things that we can do with option 3x is that data can come from core network to the 5G GNB. From 5G GNB, some data can directly go to the UA over NR air interface, and some data can be forwarded to LTE base station, and we use LTE air interface. So that is the kind of flexibility we have. So both the base stations, LTE and 5G, have signaling connection as well as traffic connection between them. LTE is the master node because the NAS signaling passes through the LTE base station. So the benefits here include faster time to market, and you can still get pretty good performance from NR air interface, and we have overall coverage that is reasonably good due to widely deployed LTE. Network functions virtualization is important. So we basically go away from physical network functions where we have individual boxes doing the functions. They are purpose-built, proprietary hardware, proprietary software, and tightly coupled hardware software. But when we virtualize it, then we do the software implementation on generic hardware. So for example, we can put the AMF software on some generic processor, it becomes AMF. So we can use generic hardware, often called COTS, commercial off-the-shelf hardware. This gives us independence of software and hardware, and the software runs on the cloud infrastructure resources, and we make use of compute, storage, and networking resources of the cloud infrastructure. We get the benefits like cost savings, scalability, and agility. Software-defined networking is also important for deployments. So the basic idea is that we try to rely more on software to connect different nodes or network functions. So traditionally what happens is that we have an IP router that has the functions like routing table creation, packet forwarding, and now instead of doing all these functions in the same network element, what we do is we divide the control plane and data plane. So it is like divide and conquer. So control plane would centralize the intelligence to determine optimal paths, effectively routing tables, and the data plane, very simple, it simply forwards the packets. So we separated the signaling from traffic. So now we can use very simple SDN switches or networking devices. So what are the benefits? Well, since we have centralized the intelligence, then we can make better decisions because we know what is happening in different parts of the network. We minimize the manual configurations of routers, and of course we reduce the cost because data plane devices are very simple. Spectrum, very important for 5G. So in phase 1 we have frequency range 1 that is below 6 or 7 gigahertz, and we have defined FR2 to cover approximately 24 to 53 gigahertz. In general, millimeter wave means we should have 30 gigahertz or more frequency, right? But in practice, even if it's 24 gigahertz, we say it is millimeter wave spectrum. So if you look at license spectrum, could be below 1 gigahertz. For example, operators have 600 megahertz deployment. Then we have 1 to 6 gigahertz. That is mid-band kind of spectrum. And then we have millimeter wave spectrum above 6 gigahertz. A variety of frequency bands. So there are several benefits and challenges. If you have lower frequencies, we get better coverage, but channels are narrower, so throughput is low. If you have a millimeter wave spectrum, you have so much spectrum that your throughput is high, but because of large path loss, coverage is smaller.
So let's summarize what we've learned. 5G supports enhanced mobile broadband, ultra-reliable low-latency communications, and massive machine-to-machine communications. 5G has much better specs than 4G, and note particularly the latency is much lower than 4G. The 5G next generation RAN includes its base station, G Node Bs, and also the core network is comprised of network functions such as AMF, SMF, and UPF. Network slicing is one of the neat features of 5G, allows custom logical networks to be created to support a variety of quality of service and customer requirements. The new radio interface includes such features as massive Mimo, different OFDM numerologies, as well as different framing structures for the OFDM, and it operates over diverse spectrum, and it has advanced channel coding. The standalone new radio architecture is the ultimate. It works with the 5G core. However, currently, we're mostly deploying the non-standalone architecture, in which the new radio needs the old core network, the EPC, and it needs a LTE base station to act as the master node. 5G operates over a very large frequency range. While the lower frequencies are used to provide coverage, the higher frequencies, such as the millimeter wave range, provide higher throughput. Mobile edge computing places the application closer to the users, and that's one of the key reasons why we're able to reduce the delays in 5G. The service-based architecture defines interfaces and facilitates a modularization and virtualization of the core network. SDN is very helpful in improving the routing and reducing cost. And finally, network function virtualization enables software implementation of a network function using very generic commercial off-the-shelf hardware.
Thank you again, Professors Reed and Tripathi, for that extremely informative presentation. Next up is Jeffrey Chahanski, who will provide us with information about 5G standards. Mr. Chahanski is an information technology specialist at the National Institute of Standards and Technology, working in the Applied Cybersecurity Division of the Information Technology Laboratory. He's an active member of the 3GPP's SA3 working group, which he'll explain in his presentation, and he has been engaged in the development of 5G security. So now we will roll the second tutorial video, which is 5G standardization, 5G security enhancements, and supporting infrastructure security considerations.
Good morning, everyone. My name is Jeff Chahanski. I'm a researcher in the Information Technology Lab at NIST. And this morning I'm going to talk a bit about 5G standards, specifically 5G security enhancements that come with the 5G standards, and some of the supporting infrastructure security considerations. I want to say thank you to organizers for including me on this morning's tutorial session. So when we talk about 5G standards and standardization in general, it's important to understand that there's many different standards development organizations, or SDOs. Many different SDOs are responsible for defining and specifying different pieces of the 5G system. Specific examples are the Internet Engineering Task Force. They define critical internet protocols like TCP/IP, TLS, things like IPsec. A lot of their protocols are used heavily in the 5G system. There's ETSI, the European Telecommunication Standards Institute. They do a lot of work in various different technology standards, but specifically virtualization is very important, and different ICT standards as well. And then there's the Institute of Electrical and Electronics Engineers, the IEEE. They're really critical. They've defined the 802.11 specification, or otherwise known as Wi-Fi, and they're doing other work related to 5G. But specifically for 5G, the main group that's defining how the 5G system works is the Third Generation Partnership Program. They've defined 3G, they defined LTE or 4G, they defined the voice over LTE that LTE brought with it, and now they're working on defining 5G. So we're going to dive in a bit about 3GPP because that's kind of the relevant standards developing organization for 5G, and really the group where the meat of the 5G system is being defined. So 3GPP is really defined as a global initiative, and they're responsible for mobile communication specifications. So they call themselves a global initiative because they're made up of partner organizations or regional SDOs. Examples of these SDOs are ETSI in Europe, Arab in Japan, ADIS in North America, and the makeup of all these developing organizations, these standards bodies, contribute to the Third Generation Partnership Program. So in order to contribute to 3GPP, you have to be a member of one of these regional SDOs. So kind of the really short, too long didn't read, 3GPP is writing the technical specification for 5G. They're defining the interoperable interfaces, the protocols, and the security features, which we're going to get into a bit more today. And just a little timeline, 3G was defined by 3GPP in Release 3 back in 2000. 4G or LTE defined by 3GPP in Release 8 back in 2009. The first version of 5G, known as 5G non-standalone, was released in 3GPP Release 15 in 2017. And a few months ago, we finally frozen the 5G Phase 2 or Release 16 specification. So to continue to talk about 3GPP and kind of the organizational structure, it's kind of important to understand they're made up of three overarching groups. Specifically, the Radio Access Network, or otherwise known as RAN, the Service and Systems aspects, commonly referred to as the SA groups, and the Core Network and Terminals, or referred to as the CT groups. So each of these groups kind of has a plenary group that's oversees the sub-working groups, and they're responsible for setting the priorities, the timelines, and the coordination that's happening within each of these technical working groups. So specifically, for the past 4 years, I've been an active delegate in 3GPP's SA3 working group. This is the group's responsible for defining the security architecture. When I started attending 3GPP meetings was when 5G security architecture was kind of a blank page, and we were just beginning to lay out how the 5G security architecture is going to work and what security features would be included. A little more to continue on about 3GPP and kind of how the group works. A little more specifics about RAN. They're really responsible for defining all things radio interface. They define the really hard technical aspects of the radio access network. They're responsible for advancing the state of technology and how we're able to send more bits over the limited spectrum we have available. The SA groups are really responsible for the overall architecture and services capabilities of the system, from requirements to general architecture to kind of specific security architectures. The CT groups are responsible for specifying terminal interfaces, kind of the logical and physical interfaces, the different terminal capabilities, and the core network parts of the 3GPP system. If you look at CT, they're the folks that take the high-level specifications and boil them down into the bits and the bytes and actually standardize what each message and each bit needs to look like. Another important component of 3GPP is they work using a 3-stage methodology, and that's applied within the working groups as follows. Kind of stage 1, overall service description from the user standpoint. Really high level, coming up with requirements and what are some of the services that the new release of 3GPP system should have included. Stage 2 is the overall description of the organization of the network functions to map service requirements into network capabilities. So a lot of the architecture stuff is happening in stage 2. And stage 3, a lot of times, is where a lot of the CT groups comes in, and it's the definition of switching and signaling capabilities needed to support the services defined in stage 1. So really or stage 3 is really writing the hard zeros and ones that go into making the system operate. So just some insight into the 3GPP process. As I said, I participate in 3GPP SA3. Each working group is a little bit unique. So my perspective is kind of an SA3 perspective, but the general approach is you study new features, new capabilities, new things you want to include, and then potentially the next release. From a security perspective, this could be studying security issues or security features that are seen as important. And then kind of the outcome of those studies are made into the technical specifications in the form of normative work, which is actually making it into an actual standard. So the TR really, from an SA3 perspective, the technical report, or TR, presents the different solutions for a specific problem or capability. And a lot of these times we're leveraging protocols and capabilities and technologies from other standards organizations. So as we mentioned, IETF and IEEE, 3GPP relies heavily on technologies defined by other standards organizations to make the system work. There is definitely roles and responsibilities for each of these SDOs, and they try to utilize each other's technologies as much as possible. The work really happens in an iterative pipeline. SA3 defines solutions based on SA1's requirements and SA2's architecture. And also for mission critical services that are defined by SA6. There's a lot of tight timelines that require the groups to really work in parallel, and sometimes rework is required. If an architecture changes from SA2's perspective, that means the security solution for that architecture might also need to change or evolve. And then SA3's security solutions are really made real by CT1. So they take the high-level security architecture and implement it in the overall system in kind of that really detailed bits and bytes level. And then a really important notion for 3GPP is it's a consensus-based process. So the idea is all individual contributing companies bring contributions. Those contributions are discussed at a very technical level. They're argued, they're disagreed with, they're agreed with, they're promoted, and sometimes they're kind of not looked on with much seriousness if it's not a real technical solution. So it's really hard to kind of just barge into a 3GPP meeting and try to push your solution to a specific problem, because it needs to be really informed at a technical level, and it needs to make sense within the system. So these technical discussions, resorting to a vote is really rare. It's kind of seen as a failure of the process. And voting is, from an SA3 perspective, really what I've seen has been reserved for electing the leaders of the working group. Just a quick splash of the current timeline. You can see Release 16 has been frozen in June 2020. Release 17 is underway in many of the groups, and Release 18 is beginning or already has begun in some of those stage 1 groups. So we're going to shift a little bit and talk a little bit about network security and just the overall security capabilities that 3GPP and 5G bring to bear in this new generation of cellular network. So just the super basics, we have a device, it's connected to a network of base stations. That network of base stations or radio access network is then connected to a packet core of some kind. And then that packet core provides connectivity out to different IP networks, whether that's the internet or some specific other IP network that needs to be connected up to. So super high level, diving in to overlay some security around that. An important component of 3GPP and mobile network security is provided, but it's provided at a hop by hop level. It's not defined to be end to end. There's no security from the 3GPP system perspective from my device all the way to the internet. The security happens at each hop of the network. So in the radio access network, I have access stratum security. There's NDSIP or network domain security used, which is a 3GPP term for IPsec. NDSIP is used between kind of the radio access network and the core network. And then there's also non-access stratum security provided from my device into the core network to protect a lot of the signaling traffic that happens. So just the key point is security is provided. It's provided at a hop by hop layer. This is just a good representation of kind of where security exists. So we have user plane security. We have AS security or access stratum, protecting the control plane from the radio network. And we have non-access stratum security that's protecting the signaling of the core network traffic. There's NDSIP or IPsec, and then there's TLS provided at multiple layers of the system. So to overlay, you can see that user plane security and kind of the radio control plane security is terminating through the base station. And then we have security protecting core network signaling going from the UE into the 5G AMF or CIF. And then we have NDSIP used to protect different portions of the network as well. TLS is becoming widely used within the different functions of the core network. And then over top of all of that, from an actual application perspective, a lot of our applications and our apps and our organizations, we have user plane application layer security that is providing kind of an overall layer of security from end to end, taking advantage of all of the baked in mobile network security and layering on top of that. So that was kind of a high level of where security is in mobile networks. That relevant for LTE, it's relevant now moving forward for 5G. So as the standards were defined, there's definitely some known security issues with LTE. The technology has been around for 10 years. It's not perfect. Just some inherent ways in the way the network was designed allowed potential attackers to do some subscriber tracking based on information that was sent over the air in the clear. In LTE, based on the key hierarchy, there was no possibility of user plane integrity protection, so no way to protect user plane traffic at that 3GPP system layer. There were definitely some roaming issues. I'm sure folks are familiar with SS7 and diameter threats, taking advantage of weaknesses in some of those networks. And then kind of general false base station threats are definitely a real thing with any kind of RF technology. So moving forward, 5G, the goal really was, from a standards perspective, was to build on the security provided in LTE. LTE had robust security protections. Just because there were some known issues doesn't mean it wasn't a robust, secure system. But the engineers that were defining the 5G security architecture in 3GPP understood some of those security weaknesses and really aim to improve 5G security. So we like to say 5G security is really an evolution of LTE security. It's not a revolution. It's building upon some of the good stuff that was already there. So some of those specific features that we have are user plane traffic integrity protection. As I mentioned, that didn't exist in LTE. It's now possible with 5G. There's some subscriber privacy features to prevent some of those subscriber tracking threats. There's a notion of a security edge protection proxy. This network function provides standardized security at the roaming interface. There's a new authentication framework to allow different authentication methods into the network. And there's this notion of splitting out the radio unit in this centralized unit and distributed unit, so you can do some security enhancements kind of from an architectural perspective. We're going to dive into a bit of these in more detail, starting with the radio network security piece. So as I mentioned, finally we have integrity protection for the user plane. The control plane integrity protection was available since the UMTS days. And then, as I mentioned, we also have the split out of the G node B into a central and distributed unit. The CU or centralized unit performs the security critical functions, like terminating confidentiality and integrity. And the air interface security terminates at the CU. So that allows you to locate that in a more trusted environment closer to the trusted core network. There's also some language in the specification to provide increased visibility to applications to have a better understanding of what their security connection looks like. This could be really promising moving forward as the 5G system evolves. It could allow applications to query the network to understand what their security posture of their current connection is. You could picture a banking app. If you open it, the app could hit this API, understand its security connection. If it didn't meet the requirements for whatever's laid out by that application then could initiate some kind of over-the-top application layer security to protect against that kind of weak base station connection. So there's some privacy protections within 5G as well. Kind of the objectives of these were really to protect the permanent identifiers, cycle temporary identifiers in a more regularly scheduled way, a more standards-based way, and kind of avoid these re-authentication that pose some threats in previous generations of 3GPP systems. So the big thing that comes up when we talk about 5G and 5G security is the encryption of the subscriber identity. In 5G, that subscriber identity is known as the SUPI. In LTE, that subscriber identity was known as the IMSI, and I'm sure folks are familiar with IMSI catching threats. So now the 5G system allows you to send this subscriber identity over the air in a concealed manner, so it's no longer sniffable or catchable by a rogue base station or just malicious actor. There's some 5G authentication framework enhancements as well. So the credential storage, we have storage on secure hardware, whether that's a removable UICC SIM card or if it's an embedded element in the device, like something commonly referred to as an eSIM. You can have the same authentication method to access both 3GPP and non-3GPP access. So picture connecting to Wi-Fi using a 3GPP kind of security or credential. There's also native Imt support for 3GPP access. So this could allow in the future things like IoT devices to take advantage of Imt TLS to prevent them from having to have that physical SIM card and allow a more scalable deployment of authenticating IoT devices on the network. So one critical thing I like to talk about that's really important from a 5G security perspective is the 5G network is really comprised of many components utilizing different modern IT technologies. 5G is moving from a legacy kind of network functions as a physical box to a more softwareized cloud native approach to the system. The packet core network functions are really being written in a cloud native way using things like containers and container orchestrations to manage and operate how the system works. So taking advantage of modern technologies, the network functions are really one piece of that 5G system. The network functions are going to operate on top of kind of general purpose IT components, things like cloud computing technologies, cloud operating systems. They're going to utilize virtualization and container orchestration. So it's really important that you look kind of below the 3GPP network function perspective and look at that supporting infrastructure and apply and understand what the cybersecurity best practices that can be used for those various different components of the technology stack. There's a lot of best practices that exist for these technologies. These technologies are widely used in the IT space. So it's really important that you're turning on and enabling the capabilities from a security perspective that exist in that supporting foundational infrastructure layer. And just to build on that a little bit, there's many different technologies and protocols being used. I mentioned cloud computing technologies, but it's also important to note that internet security protocols are being widely used as well. And these protocols, as I mentioned, are specified by other standards developing organizations, things like IPsec, TLS, JOSI, many other IT security protocols are being used in these systems. So it's important to understand what the best practices and the best ways to deploy those types of technology are. So if you have any questions or comments, feel free to reach out to me. My email address here, Chahanski@nist.gov. I really appreciate everyone's time today, and I hope you enjoy the rest of the conference.
Thank you, Jeffrey Chahanski, for that very informative overview of the standards process. I'm actually looking forward to asking you some questions during the Q&A period. We will now learn about Spectrum for 5G within the United States from Dr. Monisha Ghosh, the current Chief Technology Officer of the Federal Communications Commission. Dr. Ghosh is also a research professor at the University of Chicago. And prior to joining the FCC in January of 2020, Dr. Ghosh served as a program director at the National Science Foundation. So our third tutorial video is Spectrum for Next Generation Wireless, 5G, and Wi-Fi.
Good morning, everyone. First of all, I'd like to start off by thanking the organizers for providing me the opportunity to spend a few minutes discussing FCC's priorities in allocating spectrum for next generation wireless, both 5G and Wi-Fi. My name is Monisha Ghosh. I'm in a temporary position at the FCC as the Chief Technology Officer. I'm also a research professor at the University of Chicago, where I conduct experiments and research on 5G and wireless. So the topics I'd like to cover in the next few minutes start off with the spectrum landscape for both licensed and unlicensed. As we are all aware, both of these parallel technology paths for wireless deployments have been progressing very rapidly over the last few years. Each of them have designed and specified system designs that are increasingly higher rate, lower latency, providing better quality of service. And in order to do this efficiently, both systems need larger and larger spectrum allocations. So we'll talk a little bit about where we think the spectrum can come from. Then I will move into a discussion of the licensed regime, talk about spectrum allocations in high, mid, and low bands. All of these three spectral regions are very important in order for us to get a complete user experience. I will also talk about unlicensed, even though one does not think about unlicensed spectrum as where licensed technologies like the Gs, 1 through 4 and 5G will be deployed. It is increasingly clear, especially as borne out by the deployment of LTE LAA in 5 gigahertz, that cellular technologies will take advantage of the unlicensed spectrum to deploy their systems in a way that they can aggregate channel capacity to give a better end user experience. So there are two actions in this area that I would like to talk about. One is a 6 gigahertz draft report and order, and the second is the repurposing of the 5.9 gigahertz spectrum. No talk on spectrum is complete without this picture, which many of you have probably seen in the past. This basically gives you the United States frequency allocations. While this is specific to the US, similar charts exist for every country in the world, and they're all similarly crowded. The bottom line is that spectrum is scarce. It is a finite resources. And as you can see from all the little colors and the bars on this chart, it is pretty much allocated, especially if you look at the regions that have been used the most for consumer communications, which is somewhere up until 30 gigahertz. You see your familiar services there, your AM radio, AM FM radio and television, and then the cellular and Wi-Fi services. This is not a complete depiction of everything that has been allocated so far, but it just gives you a general sense of how little of the spectrum that's out there is actually used for the services that all of us have come to depend on. The other thing I should point out that a large part of these spectrum bands are allocated for federal use, and those have usually been off limits for up until now, but increasingly sharing with federal services or finding ways to coexist with them is becoming an important part of the spectrum strategy for not only the FCC but other regulatory bodies around the world. Now, as you can see from this picture, as you're going from the chart from top to bottom, the scale changes. It's not a linear scale. And so the same area covered by a circle at the bottom of the chart actually encompasses a larger swathe of spectrum. So the 60 gigahertz Wi-Fi circle is actually 14 gigahertz of spectrum in that little circle there at 60 gigahertz, which is more than all of the allocated spectrum, say below 3 gigahertz, obviously, right? So basically what this tells you is that if you're looking for more bandwidth, more spectrum availability, you need to go higher in the spectrum band. But at the same time, as you go higher, you face the problems that physics poses in terms of propagation. The signals don't travel very far, and so it has to come with accompanying change in the way you design your cellular systems or Wi-Fi systems to operate at these higher frequencies. I'd like to now talk about the FCC 5G FAST plan. So this is FAST stands for Facilitate America's Superiority in 5G Technology. You can either Google the FCC 5G FAST plan, or if you go to the website there, what you will see outlined there is a very comprehensive strategy of how the FCC plans to allocate spectrum in high, mid, and low bands, as well as in the unlicensed band in the service of future 5G and advanced wireless services. In the high band, which I denote as greater than 24 gigahertz, this is where one expects the 5G millimeter wave variant to be deployed. Again, because this is much higher in frequency, propagation losses, propagation inherently limits the distance that you can cover with a single base station. This lends itself to small cell deployments. However, the bandwidths are much, much higher, and so you have the potential of actually getting gigabits per second throughput in these frequency ranges. In fact, as part of the research that I do at the University of Chicago with my students, we've been taking a lot of measurements on Verizon's millimeter wave deployment in Chicago, 5G deployment, and we have measured download speeds of 1 to 1.5 gigabits per second, depending on where we are located. However, purely focusing on the high band is not an effective way of rolling out 5G for everybody. The mid band plays a crucial role in getting 5G out to everyone. It is a nice balance between coverage and throughput. The frequencies lend themselves to wider deployments, and there is enough bandwidth there to get reasonable throughput as well. So this is very, very important for any wide-scale mobile wireless system to have mid-band allocations. I will not spend a lot of time talking about low band, which is less than 1 gigahertz. This frequency has been mostly allocated for broadcast television in the past, but over time, more of it has transitioned over to mobile wireless, especially with the transition to digital TV. The spectrum was repacked, leading to some auctions of some channels and other channels which are being repurposed for 5G applications. Now, do keep in mind that the bandwidths that are available at these low bands are pretty narrow, so you're not going to get the high throughput that one expects when one talks about 5G. But on the flip side, you will get very wide area coverage, and this would be great for the next generation of IoT applications, for example, where you need, for example, city scale IoT, where you need large ranges, but your data rates are not that high. I will also talk about the actions that FCC has taken in unlicensed to enable not only expansion of Wi-Fi, which is the first technology one thinks about when you're thinking about the unlicensed spectrum, but also, as we've increasingly seen in 5 gigahertz, unlicensed spectrum is also a great place for cellular systems to deploy as long as they meet the rules of unlicensed spectrum. We've seen deployments in Chicago, for example, where cellular carriers are aggregating up to three channels in the unlicensed band to enhance the throughput that they deliver to their customers. And we fully expect that the new unlicensed spectrum will be used by 5G and are unlicensed in the same way as well. Oftentimes in industry, you see these two technologies set up in a competitive manner. While it is true that they occupy different spaces, we also feel that we need to allocate sufficient spectrum to both, because advances in one enable advances in the other. If you're at your home with a very high-speed Wi-Fi connection and you're used to that kind of a user experience, you expect the same level of service when you step outside the home, where of course Wi-Fi is not going to provide you that experience, but cellular will. And so we view both these systems as pulling each other up, and the consumer benefits, and allocating enough spectrum for both is a very, very important part of the FCC strategy. So let us take a little bit of a deep dive into what FCC has done on the high band. A number of auctions have been completed already. In January 2019, 800 megahertz was allocated in 28 gigahertz, 750 megahertz in May of 2019, and 24 gigahertz. And just recently, earlier this year, 3.4 gigahertz of spectrum was allocated in the upper 37, 39, and 47 gigahertz. Now, the earliest spectrum allocated was just last year, and we're already seeing 5G rollouts happen in the spectrum. So the industry is just waiting for spectrum to get allocated for them to start rolling out systems. So the total of 4.95, almost 5 gigahertz of spectrum has been allocated for millimeter wave based 5G. I believe the US now leads the world in high band licensed allocations, and this has resulted in an extremely aggressive rollout of millimeter wave 5G across the US. And as I mentioned before, this is the band where you're going to get the gigabits of speeds that we have come to expect of 5G. On the mid band, there's a lot of actions that have been done and more that are being planned. The 2.5 gigahertz is actually an interesting band. Is the single largest contiguous block of spectrum below 3 gigahertz. It's currently allocated to educational broadcast service and the broadband radio service. The FCC has an NPRM out to reevaluate the spectrum and to say what are the current needs that of these two services, EBS and BRS, and then any spectrum that is left over, there's an anticipated auction that will begin in early next year. Again, this is the mid-band spectrum, which has the nice characteristics of both propagation and sufficient bandwidth. The C-band report and order, which went out earlier this year, will result in a public auction of 280 megahertz of spectrum in the 3.7 gigahertz band. So this is 3.7 to 3.98 gigahertz. This is slated to start in December 2020. as if you remember the chart that I showed earlier on, where you see how crowded the spectrum is, most of the time going forward, if we are trying to free up spectrum in the mid-band in particular for 5G, we have to look at what's already in there, because there really isn't any spectrum that's sitting there idle. So in this band in particular, you have satellite incumbents, which have to be moved out of these 280 megahertz of spectrum. They will continue to operate in the upper 200 megahertz, so 4 to 4.2. There will be a 20 megahertz of guard band between the 5G mobile, terrestrial, and satellite. But that takes time. There is also a process by which the satellite incumbents are paid to move out of the spectrum. And the money for that comes from the proceeds that the auction will raise. So licensing spectrum in the mid-band is usually a longer process than, say, the high band, where there was a lot more available spectrum. And we're going to see this repeat in other bands that we pick up for 5G as well. CBRS has been in the works for many years now. This is the 3.55 to 3.65 gigahertz band where Navy radars operate. The auctions were supposed to have started in June. They slipped by about a month due to COVID, but they have begun. This auction will be for the priority access licenses. So CBRS is a band which is not only being shared by Navy radars through SAS or AFC service, but is also going to have 3 different priority classes of service. So it's the incumbents, then the priority access license, and then the general access category. So the licenses being auctioned today are for the priority access licenses. This will probably be in the US the first mid-band 5G rollout that happens, and the industry is very excited about it. There are a lot of different use cases being planned for this band. For example, private 5G networks is one thing that you can see rolling out here. And also just early 5G mid-band deployments. We are also investigating potential sharing in the band right below the 3.55. So this is the 3.45 to 3.55 gigahertz band, which also has a lot of federal use right now there. NTIA came up with a report on spectrum sharing earlier this year, and we are in the process of refining some of the assumptions and parameters to really understand under what conditions the spectrum can be shared. So there are a lot of actions in mid-band, and we hope to be able to get a fair amount of spectrum into the hands of 5G providers fairly soon. Low band, as I said, I'm not really going to talk a lot about. There is a 600 megahertz band. There's about 70 megahertz of a licensed spectrum that has been allocated there. And in 900 megahertz, there is some discussion about repurposing part of the band to enable broadband using LTE for beginning, for start, and then possibly 5G into the future. Finally, let me talk about unlicensed. We recently concluded the biggest unlicensed allocation for, that is, I think this is the biggest that has ever been done, is 1.2 gigahertz of spectrum has been allocated for unlicensed use in the 6 gigahertz band, which is basically 5.925 to 7.125. Now, unlike the 5 gigahertz, or at least most of the 5 gigahertz, this is not a clean band. As again I mentioned before, there's very little clean spectrum left. It will be shared with existing incumbents. So there are 6 gigahertz fixed links and broadcast auxiliary services there, which provide services like wireless news gathering. However, FCC has been very careful in crafting rules that will permit low power indoor Wi-Fi devices or unlicensed devices without any automatic frequency control to coexist with these bands. We have created power limits that we feel will not create harmful interference in most cases to these links. There are also going to be higher power outdoor links that will be allowed that will use an automatic frequency control system to coexist with the existing links. We really, even though a lot of the rules were crafted with keeping Wi-Fi usage in mind, we fully expect that 5G NRU will make full use of this band as well. And given that there is a lot more bandwidth here, we feel that the coexistence problem will not be as severe in this band as it has been in the 5 gigahertz band, simply because there will always be more channels that these systems can choose to operate on without interfering with each other. We expect systems that get deployed in this band to use higher bandwidths. So Wi-Fi, for example, is been moving to higher and higher bandwidths. They're at 160 megahertz now, and they're moving towards 320. We fully expect that the higher bandwidth systems will find a home here, and that the band will not get cluttered by a lot of legacy coexistence issues with lower bandwidth devices, which can still continue to operate in the 5 gigahertz unlicensed. We're also right now looking into repurposing the lower 45 megahertz of the DSRC band, which had been allocated for intelligent transportation systems. This band has been very underutilized for the last 2 decades since it was allocated. And given the growing needs of Wi-Fi, the FCC has a plan to repurpose the lower 45 megahertz of this band for unlicensed and keep the upper 30 for ITS services. The lower 45, when combined with existing spectrum in the 5 gigahertz, will create wideband, at least one wideband channel that can be used by both Wi-Fi as well as for LTE, LAA, or 5G NRU kind of services. At the same time, we've allocated 21.2 gigahertz and 95 gigahertz band for unlicensed use. Above 95 gigahertz is where there is a lot more availability of spectrum. There is a lot of passive uses of spectrum there, which have to be managed. And we've made very easy experimental license availability in these bands. And we really hope the academic community in particular will utilize these resources to push the boundaries of where we can go for the next generation of wireless systems. I'll end with some closing thoughts about what a sustainable spectrum strategy is. I don't expect you to read everything that's on this slide, but I just want to point out how often the word sharing comes up in this presidential memorandum on developing a sustainable spectrum strategy that was released in 2018. So as we go forward, we expect to see more and more spectrum being allocated either on an unlicensed or a shared license or some kind of shared basis, because the bottom line is very little clean spectrum available for all the services we are interested in. Thank you for listening, and I hope to have an engaging conversation at the end of this tutorial session. Thank you.
Thank you very much, Dr. Ghosh, for that excellent presentation. Finally, Dr. Mohamed El-Moghazi will walk us through 5G from the international perspective, including explaining the relationship between 5G and IMT 2020. Dr. El-Moghazi is the Spectrum Management Research and Studies Director at the National Telecommunications Regulatory Authority, NTRA of Egypt. He's currently coordinating several items for the WRC-23 in Egypt. He founded the Global Telecom Policy Research Network, which is an initiative for scholars in telecom policy, and authored numerous articles. We are thankful that Dr. El-Moghazi is able to join us virtually. So here we have our fourth and final tutorial video entitled IMT 2020 Spectrum Identification and Technology Standardization.
Hi everyone, this is Mohamed El-Moghazi. I'm working for the Telecom Regulatory Authority of Egypt as Executive Director of National Spectrum Affairs. I'm also responsible of several related issues to 5G at the ITU on behalf of Egypt and the Arab region. First of all, I'm very glad to have this opportunity to participate in this conference, and I'm very grateful to the conference management, especially my mentors, Professor Dale Hitfield and Dr. Pierre DeVry. Secondly, you may wonder if this conference is about 5G, why this specific presentation address what is called IMT 2020. In fact, within the ITU, the International Telecommunication Union, the international community address many issues related to 5G and sometimes lead it, but in order not to have a conflict with commercial deployment and the names of the different cellular mobile generations, 3.5G, 4.7 5G, it was decided, at least within the radio sector of the ITU, not to use the abbreviation of 2G, 3G, 4G, and 5G. And instead, we call it all IMT, International Mobile Telecommunications. And the different generation names are not recognized within the ITU. Also, the ITU is different as an international forum from organizations such as 3GPP, ETSI, and the IEEE, as the process is inclusive for all countries with equal vote. That enables several people from the developing countries, including me, to have a big say when it comes to the technology and frequencies associated with it, which are the topics that we will discuss today. So, IMT. To give you an idea of how IMT was developed, let's read this quote. The ITU is currently working on one of its most ambitious projects ever, system standards for third generation mobile telecommunications, coined the IMT 2020. It will make it possible to communicate anywhere, anytime. That quote was recorded in 1998, and it gave you an idea what the ITU wanted to make at that time. Remember, we are talking about the 3G era. And in fact, the IMT idea was the ITU reaction towards the lack of interoperability between second generation mobile standards, in order also to get more involved in the standardization process of mobile system. I believe many of you remember the rivals between 2G different technologies and the discussion on whether CDMA or GSM is better. The ITU is involved in two main processes. One of them is related to the technology standardization, and the other one is related to the frequency use associated with these standards or technology. The first process has resulted in different generations of IMT, which are also related to the generations of cellular mobile technology, namely IMT 2000, IMT Advanced, and IMT 2020. All these generations are treated equally in terms of the spectrum identifications and are called IMT. The second process is called Imt Spectrum Identification. And firstly, we should understand that the ITU mainly allocate the radio spectrum to the different radio communication services, broadcasting, mobile, and fixed. But in the case of cellular mobile, the ITUR radio regulations perform what is called the identification, which is a second process to allocating the band for mobile service. Identification indicates some sort of inclination or tendency towards utilizing these identified bands for IMT. Anyway, it's worth mentioning that it's not usually within the ITU to have identifications to specific technology. But certainly, there is a global desire in having more certainty in developing IMT system. So, the first step in the ITU standardization activity on mobile technologies was in the 80s, when the concept of future public land mobile telecommunication system was discussed in the ITU due to the support of European countries that were seeking a successor to GSM. And then the idea of IMT 2000 emerged to reflect that the mobile service would use the 2 GHz spectrum band and be available in the year of And in the year 2000, 5 systems were recognized by the ITU after extensive evaluation to be part of the IMT 2000 family. In 2007, a big milestone when the IEEE WiMAX technology was accepted as the 6th IMT 2000 system. 2008, ITU started the process for what is called the IMT Advanced at the time of the 4G era. 4 years later, 2 main technologies were recognized as part of the IMT Advanced family, namely LTE Advanced and Wireless MAN Advanced. Commercially, these systems were called the LTE and WiMAX. 2016, the ITU started the process for what is called the IMT 2020, which is related to the 5G technologies. The process has started in 2016 and has not finalized yet. In other words, until today, there is no recognized technologies by the ITU as IMT 2020 or what is called commercially as 5G. So let's start digging to understand where it all starts for IMT 2020. The beginning was to have a vision of what should IMT 2020 system performance looks like. And this famous diagram that you may have seen it in several other presentations, it was originated by the ITU as a vision on how the IMT 2020 should succeed IMT Advanced and in which aspects. Clearly, one main element was peak data rate, and the minimum requirements were set to be 20 gigabit per second for downlink peak data rate. Another important element that was set is download user experience data in practice, in contrast to the theoretical big data rates. And it was agreed that such value should be around 100 megabit per second. The third important elements that reflect how IMT 2020 would be different than IMT Advanced are the latency, which was agreed to be less than 1 millisecond. And let's not forget about the connection density also. These two elements show the usage scenario of 5G that required very low latency and are implemented by massive number of devices. In this slide, I'm trying to elaborate to you what has been the timeline for IMT 2020 standardization process and how it works. I'm so sorry for the small details, but anyway, the standardization process accommodates some main milestone. Firstly, the ITU issued an invitation for technology developers around the world to propose technology standards that meet the IMT 2020 performance characteristics previously mentioned in the last slide. The ITU issued also an invitation for external independent group to evaluate the applicants' technologies against the criteria decided by the ITU members. Following that, these evaluation groups were formed and evaluated the applied technologies. And the deadline for submitting the evaluation was last February of 2020. Last June, it was a very important meeting of the Working Party 5D of the ITU, which decided on the main IMT 2020 systems that meet the criteria as decided by the evaluation group. And in next November, the ITU will issue the formal recommendation accommodating the characteristics of this approved system. So, to this end, what were the proponents to be part of the IMT 2020 system, or as commercially mentioned, 5G? I know there is usually a perception that 5G is the 3GPP new radio, NR, but this is not quite accurate. In particular, there were 7 proponents to the ITU. The first is the 3GPP SRIT, or Set of Radio Interface Technologies, which accommodates the new radio in addition to the EU TRA, Evolved Universal Terrestrial Radio Access, or the LTE. The second is the 3GPP Radio Interface Technology, or the new radio. And the third is or was a proposal from South Korea, which is identical from the technical point of view to the 3GPP RIT. Fourth proposal is from China, which is also technically identical to part of the 3GPP RIT, and have another identical part, which is narrowband IoT, to the 3GPP SRIT. The fifth proposal is Telecommunication Standard Development Society of India proposal, which utilize the 3GPP 5G new radio, but also adds functional capability to support low mobility large cell in rural areas, and it's perceived by its proponent as quite appealing to the developing countries. Sixth proposal is by DECT Forum and ITSI, and it's called DECT 2020 New Radio. And the last proposal is a New Front, which is a proposal from a Chinese company. So, as I mentioned, there was an important milestone in last June of 2020 where only 3 main technologies, or 5 main proponents, if you include the proposal from China and South Korea, that proceeded to the final step, or step number 8, which is the development of radio interface recommendation. However, there was a big debate on the way forward for the other 2 proponents, New Front and the DECT Forum and ITSI. And it was decided that these 2 technologies need additional evaluation. So as I mentioned before, the Imt standardization process has been associated with identifying the radio spectrum bands to be used by these Imt standards. The first step was in 1992 when the World Administrative Radio Conference of 1992 identified the 2 GHz band despite of opposition from countries such as the US. 8 years after that, the World Radio Communication Conference of 2000 agreed to identify the bands 900 meg, 800, 1800, and 2.5 giga for IMT. That decision was a big boost for the harmonization for IMT, considering that the band 900 was used mainly for 2G. WRC of 2007 was quite important in identifying additional bands needed for the growth of the mobile industry. And then the WRC of 2012 achieved global harmonization between the 3 ITUR regions in the UHF bands. And surprisingly, that was in response to requests from the developing countries in Africa and the Middle East. WRC 15 identified more frequencies for IMT, and I think one of the most important band is the UHF. From 470 to 694 in the United States and few other countries. And finally, the WRC of 2019 that was held last November in Egypt identified 17.25 gigahertz of spectrum compared to 1.9 gigahertz before the conference, of which 14.75 gigahertz are harmonized worldwide. That was a big achievement for the IMT community. So an important question: do countries usually deploy 4G and 5G systems in band identified for IMT? The short answer would be no. As you can see in the displayed table, there are 4 cases that I can count where there were IMT deployment without IMT identification. So the L band or part of it, for instance, is not identified in SIP countries for IMT, but still used for IMT. Similarly, apart from the C-band, is not identified for IMT, and not even, and doesn't have even a primary mobile allocation, but still used for IMT in Europe, in SIP countries, and in some of the Arab countries. The 26 gigahertz, although it was identified at WRC19, several countries decided to utilize it for IMT without waiting for the conference and before the conference. And finally, the famous 28 gigahertz is not identified for IMT by the ITU, yet it's still used for IMT in several countries, big countries, including the US and Japan. So, a second question, why countries seek IMT identification to deploy 5G? Well, being recognized by the ITU provides greater certainty against interference and is based on international sharing studies. And certainly it also ensures protection for existing service. But on the other hand, why other countries deploy 5G without IMT? Such as the case of 28 gigahertz. Well, this is related to having less deployment conditions, and faster deployment. Of course, this is conditioned by having support from the industry. So, I look forward for the World Radio Communication Conference of 2023 and what is at stake for the 5G or IMT community. I think we have 4 main agenda items that are critical, and we need to understand and get a view on them. The first is agenda item 1.2, which considers additional identification for IMT, including several bands in the C-band in region 2 where the US lies, and also some of these bands are in the 6 gigahertz band, where the FCC has recently opened more spectrum for Wi-Fi. The second agenda item is 1.4, where the concept is of HAPS, high altitude platform stations, is used as IMT base station in what is called HIPS. And in such case, the HAPS will act as an extension to the traditional IMT coverage. The third agenda item is 1.5, where the future of terrestrial broadcasting in the UHF band, mainly 470 to 694, will be discussed. And it will be also discussed whether the band could be utilized for IMT. Fourth agenda item is 9.1.c, which studies the use of IMT systems for fixed wireless broadband in the frequency bands allocated to the fixed service, rather than traditionally perceive the IMT as only used for mobile service. Finally, if you need more details on what's happening with regard to the IMT 2020 standardization, please check the first link. It has a lot of information, and it has most of the reference for the content in this presentation. Not all the documents on the website are available publicly, but certainly there is much more information that was presented in this presentation. Also, if you are interested in learning more about the coming World Radio Communication Conference of 2023 and the potential frequencies for 5G, please check the second link for the Conference Preparatory Meeting, or CPM, of 2023. Thanks a lot for your attention, and please feel free to email me if you need any further clarification. Thank you all.
Thank you, Dr. El-Moghazi, for that insightful presentation. I'd like to now welcome all of our distinguished speakers into the live session now to begin the Q&A portion. And first, let me, we're getting video from everybody? Thank you. First, let me thank you all again for your presentation. I'd like to start with a few questions from me to each of you before we go to the audience questions. And for the audience, please look at the questions that are already in the Q&A section on the right of the screen. and vote if you too would like to hear an answer to a particular question, and continue to add questions through the Q&A section if you'd like. I'll endeavor to pull questions based on those with the highest interest. So let me, if I could, start with a question here. So Dr. Ghosh provided an excellent overview of spectrum for 5G band in the US, and Professor Reed and Professor Tripathi both, let me ask you, did I understand correctly that the basic architecture for the 5G new radio is flexible enough to work for any spectrum band where 5G might be deployed, whether it's low band, mid band, high band, including the ultra high band millimeter wave? And I think Dr. El-Moghazi addressed this in one of his slides about IMT 2020, but just wanted to make sure that I understood that the same thing applies there for how IMT 2020 is currently conceived.
Okay, so yes? Yeah. So you might have seen acrobats in a circus. They bend their bodies in a way we cannot imagine. That is flexibility of 5G. So yes, we do support low band, mid band, high band. Even commercial deployments have already begun. So T-Mobile, just recently, couple of days ago, said that now they have a nationwide 600 megahertz 5G network. Verizon and AT&T have already deployed in the US at 28 gigahertz and 39 gigahertz, which are a millimeter wave spectrum. So yes, we already have real world deployments. Thank you.
Yes, Rebecca, if you can add. So first of all, thank you so much for those who are attending here. Rebecca has been doing a big job during the last week. So thank you so much for this. And thank you so much for the very good question that made me think about what the ITU has been doing. So yes, although the IMT 2020 are just systems of approved system for 5G, including the 3GPP 5G new radio, but it does provide some sort of flexibility in terms that the spectrum identified for IMT, whether it's in low band, mid band, or high band, could be used for IMT systems. This include any 5G, 4G, or 3G. So flexibility is provided also by the ITU. Thank you.
Great, thank you. My next question is directed this time to Dr. Ghosh. You mentioned that there's an expectation that wider bandwidths will be used for 5G. And you also talked about how with the higher spectrum bands, there's more capacity and faster throughput. So can you kind of help pull that thread together for us to briefly explain why wider bandwidths are also needed? What is it about 5G that requires so much spectrum?
Thanks, Rebecca. So as Nishith mentioned, right, so you have 5G in all flavors, and depending on the bandwidth that you deploy it in, you will get an attendant bit rate. So the wider bandwidths, and like 100 megahertz, for example, are what you need if you really want to get to close to gigabits per second throughput. We have made, the academic community and industry together have made great strides in increasing spectral efficiency, which refers to how many bits per second you can push through a fixed amount of bandwidth. And a lot of the advances you've seen in 4G in particular have come from that. However, having more bandwidth, basically your throughput scales linearly, whereas everything else, that linear scaling is much more difficult to achieve. So now if you think that you need the wider bandwidths and you look at where the wider bandwidths are easier to get, we are trying to make at least 100 megahertz of contiguous bandwidth available in mid-band as well. But that is difficult, but that is progressing. But meanwhile, those kind of bandwidths are much more easily available up in the millimeter wave. And so as we go higher up in frequency, you're going to get the wider bandwidths, you're going to get the higher data rates. Lower down in the mid-band, you're going to see systems deployed that do this trade-off between, say, massive MIMO kind of architectures that are increasing the spectral efficiency, combined with, I don't think we're going to see too many 5G systems deployed in, say, 5 megahertz bandwidths. But you do have 4G and deployed in 5G and 5 megahertz bandwidths today. So we are definitely looking at 20 megahertz and up bands for 5G bandwidths.
Thank you. My next question, I'm going to throw one over to Jeff Chahanski. You made for me in your presentation what I thought was an excellent point about security is on a hop-by-hop level and not across the entire end-to-end system for from the device to the internet. This may be a naive question, but does that security apply both ways from both the user equipment to the internet and then back also from the internet to the UE in that hop-by-hop fashion? Jeff, you have to unmute. Jeff, I can't hear you.
Yeah. So look, until he gets back.
Well, okay. Well, I was going to say I could move on to another question while Jeff troubleshoots. Okay. I'm going to try again, Jeff. I still can't hear you. Oh no, we thought we troubleshot everything here. All right. And Nishith, do you want to give it a quick go and then Jeff?
Yeah. Yes. So the short answer is yes. That hop to hop applies both directions, internet to the UE and UE to the internet. Absolutely correct. Thank you.
All right, and then one more question before I go to the audience questions, because we've got several of those that have popped up with a lot of votes on them, which is excellent. Dr. El-Moghazi, does the ITU, well, because we were just going to talk about security there, does the ITU take a view on the security and the reliability issues that this conference is about?
Thank you so much, Rebecca. So for the next question, I need a special disclaimer that this is absolutely my personal view on this. It doesn't represent NTRA or ITU or any of that. So I looked at the conference name, Spectrum and Zero Trust, and then I looked at the official ITU documents to find what is all about the security for the IMT 2020. And I found in one of the main report on IMT 2020 that, I don't know, big phrase on security. So it states in the ITUR recommendation M2083 on the IMT vision that future IMT systems need to provide robust and secure solutions to counter the threats to security and privacy brought by new radio technologies. And that's it, silent. So I guess, and again, this is very personal perspective, we do a lot of things for the future in terms of spectrum, in terms of network architecture, but are we really ready for the future? Unfortunately, at least within the ITUR, I haven't found a formal mentioning of spoofing or jamming or anything like that. They usually talk about interference, but again, unfortunately, there is no differentiation between deliberate and undeliberate or intentional interference or jamming. We usually, I don't know, suppose the goodwill of the radio receiver. This is not the case. And having said that, this conference is a must attend for me to learn about that and to try to bring some of this information back to the ITU. So long question short, I think there is a long way that we should go, at least on the international level. Thank you, Rebecca.
Thank you. All right, I'm going to jump over to the highest rated question on the from the audience right now. So this is for Professors Reed and Tripathi. So, and you focused on the benefits of 5G. Of course, there's no free lunch. So what are some of the drawbacks and trade-offs of moving to 5G?
Dr. Reed, can you start?
Yeah, I think one of the drawbacks is going to be power consumption. And sometimes, although standards have these lofty goals of achieving certain efficiencies, right now power consumption is a key issue, particularly for the service provider.
Yeah, very good. And from the non-technical side, I would like to add that we have to invest money, right? This is new hardware, new software. We have changed the new radio, right? So this is from old LTE radio to the NR radio. So the radio interface is completely different. Radio network architecture is different. We are breaking the radio into two pieces, central unit, distributed unit. So that is completely new. And the core network, you will not find any LTE network element. Everything is new. And virtualization is the way we implement. So basically we are changing everything. So that means we have to invest money, right? So that is another challenge. Cost will be also an important factor. But if you look at performance, you cannot compare LTE and 5G. 5G will give you much better performance. So from technology perspective, yeah, 5G is the way to go. But we have to balance as an operator how fast we deploy 5G and where to deploy 5G. Thank you.
I'd also say that getting trained personnel who understand 5G, because there are some major significant differences between 5 and 4G, and there's just not that many people who really understand the standard that well at this point.
Thank you. Did someone else on the panel want to say something more? Okay, so I'm going to combine one of the audience questions with one that I was wanting to ask, and that relates to the security issues that have been fixed in 5G, but then those that remain as vulnerabilities in the non-standalone deployment. And Jeff, I hope you've got your audio fixed so that you can chime in here. So when you were discussing the security enhancements with the 3GPP standards for 5G, you mentioned separate SS7 or signaling channel as an example. And I was wondering, is the enhanced security important because in the non-standalone version of 5G, we still have that separate signaling channel? And does the architecture for the standalone 5G eliminate that separate signaling channel? And then that kind of feeds into what are the vulnerabilities between the non-standalone that we're still dealing with right now. So,
yeah, can you hear me now?
Yes, thank you.
Great.
Good.
Yeah. So the question from the audience was a very good one. In a 5G non-standalone world, security is exactly as it is in LTE. All the new fancy features I talked about are really provided by that 5G core. And we don't have a 5G core until we move into that 5G standalone architecture. So with that 5G standalone architecture, that's when we get some protection from the roaming interface SS7 attacks with the security edge protection proxy that has been standardized by 3GPP. So it's a really important point that as we these initial deployments of 5G are rolled out, to understand that all the new security features that get talked about in line with in 5G in the same breath, that they're not available until we have a 5G standalone implementation.
where we can enable those features as needed by the different operators.
Yes, I would like to add for clarity, because there are different radio and core network combinations, as Dr. Reed had mentioned. So we need a 5G core network, basically. Until you have a 5G core network, or the features that Jeff not available. Yeah, thank you.
All right, thank you. I'm going to throw a request out to the back end folks here. So Matt, when we've got a question that it's high, that's listed on the most liked, if it's been answered, would you mind making a note in the chat that it's been answered, so that so it makes it a little bit easier for me to find the right questions. Okay, so the next question that we've got in the audience chat is for Dr. Ghosh, and it has to do with the spectrum sharing. And there's a couple. He's got a two-part question here, so I'll just go ahead and ask both of them to you. Spectrum sharing seems to be a key enabler, especially for CBRS. And by the way, congratulations on the status, the bids on the CBRS. So enabler for CBRS and the 5.925 to 7.125 gigahertz. Should academia revisit the large body of work on cognitive radios that was popular over the last decade? And how do we ensure that the missteps of the TV white spaces related to cognitive radio are avoided? And then the second part is, if indeed cognitive radio technology is seen as one of the enablers to optimize sharing and use of spectrum, does the FCC have a process to certify such devices that can adapt based upon the RF environment?
Thanks, Rebecca, and thanks, Ghosh, for those questions. I think as part of the academic community that participated in a large body of work on cognitive radio, I think one of the disconnects has been that a lot of the academic work was done, I would say, in isolation. So today, when we talk about sharing within the FCC, there is still gut-level distrust of completely cognitive radios that adapt based on RF spectrum sensing, even though personally, I'm a big fan of sensing. So given the situation we are in, if you look at what we did in CBRS, what we did in 6 gigahertz, we endeavor to make sharing possible by crafting our rules, which were not based on cognitive radio per se, but were based on sharing in such a way that we think interference will not occur. So for CBRS, for example, it was mainly based on exclusion zones based on where these Navy radars were. So it was kind of a combination of sensing and databases, right? So you try to figure out where interference will occur based on sensing, but then you don't leave it to the individual radios to adapt their RF on their own. So I think as we look forward for cognitive radio and how they're most likely to be implemented, the academic community in particular needs to pay, I think, more attention to the realities of how, and that goes into your second part, right? How does FCC certify that? And that, in my mind, is actually a research question too, which I would encourage the research community to also pay some attention towards. That how would you go about reliably certifying radios that are adjusting their use of the spectrum in an adaptive manner? And definitely, I think when you say revisit, I hope it's revisiting with a view to looking at what the on-ground reality is and trying to adapt to it. I think the FCC is quite open to new methods, but at the same time, when you're trying to coexist, say, with a Navy radar, right, you really have to be completely sure that whatever cognitive methods you've developed that rely solely on a device detecting and getting out of the spectrum work in a foolproof manner. So whenever you're looking at coexistence with some of these critical and life and safety kind of applications, it becomes harder. But these are important research areas that I think need to continue, and I would encourage the research community to definitely continue working on these. In terms of missteps of TV white spaces, I think we should learn from them. I think there were a lot of other things going on. This was the first time that the FCC was attempting any kind of sharing. We've learned a lot, and the fact that CBRS today has come to fruition and we're getting licenses auctioned and there's a lot of excitement does indicate that we have learned a lot in the process. But there is still a lot of, especially the certification piece does remain a problem that we struggle with.
Thank you. Dr. El-Moghazi, I guess the next question is coming in for you. In the US, some worry about 5G encroaching on other services. For example, there have been discussions or allowed arguments about interference to weather satellite observations in 24 gigahertz and GPS in the L-band. Have similar debates occurred in the rest of the world?
Thank you, Rebecca. Thank you, Pierre, for such an inspirational question. And again, I will put my disclaimer that this is very personal view. I think the US and the FCC are on the frontier line for innovation spectrum policy. And that comes at a price. So it was the US that adopted the concept of having Wi-Fi, Bluetooth operating in the 2.4 gigahertz band, usually called at the 80s as the junk band. It was the US that adopted the 5G in the 28 gigahertz. It was the US that called for flexibility in the UHF broadcasting band. And it was the US which allowed CDMA and GSMA at the time of 2G and stimulate competition. So, no, I'm not aware of any similar heated debate in other countries, but it doesn't mean that you're doing something wrong. Democracy, it's not an easy process, and it comes at a price. And yet, I think the US is able to stimulate innovation. Many things will succeed, few things will not be successful, but at the end of the day, this is the price if you want to come at the frontier line of 5G or any other spectrum policy. Yeah, thank you, Rebecca.
Yes, Dr. Ghosh.
So thanks for that, Mohamed. And just to add on to this, I think what some of these debates around 24 gigahertz and other spectrum bands are throwing up is, and again, I'm speaking, please take what I'm saying as my personal opinion and not as an FCC opinion, but I think what it shows is how important adjacent channel issues are going to be going forward. A lot of these debates are arising because we are trying to find spectrum in an already packed spectrum scenario. We are packing things together, and yes, adjacent channel issues are going to become more important. And that is where I think policy and technology and everything needs to come into play as to how we deal with this, because it's not going away, whether it's 5G today or any other system. Any spectrum we look at, we're running up against this issue about how do we handle what's in there next to whatever spectrum we're allocating. So again, a meaty research topic for academics in particular to talk about.
And I assume also particularly for not only radio navigation, now I forgot my words. The space observation sorts of frequencies and devices, like our.
Yes, and I think the passive, protecting passive users is really, really hard, and that is something where I think we really need better technical solutions as well as policy angles to address those kind of interference issues.
So, Rebecca, you were talking about, I think, about the EESS services in the 24 gigahertz. And I'm aware that in the US you had a very hot debate on this, but I would encourage, participants to look at what's been going on in the ITU. So perhaps US or FCC view was opposed within the US, but it's adopted by other countries outside of the US, which means that it's mostly valid. So yeah, thank you.
Thank you. I want to ask Jeffrey, I think, a question on this one. So in both, Jeffrey Cichonski's presentation, you mentioned the various standard development organizations that are working on the 5G related matters. And you also mentioned the IEEE 802.11 Wi-Fi standards. And then Dr. Ghosh in her presentation also mentioned how important Wi-Fi is for 5G for spurring innovations for both licensed and unlicensed. So can you, either one of you, maybe speak to how these different standard bodies ensure that the intersections between their standards actually work?
Yeah, I can take a stab at just scope of work from a standards perspective, assuming you can still hear me.
Yes, thank you.
Yep, great. So all these different standards organizations obviously have different missions and objectives of what they see their scope of work being. As we work through issues, technical issues in a group like 3GPP-SA3, we understand that there will be an intersection where we want to utilize a protocol that might be defined by different standards organizations. So there's a process through exchanging very formal liaison statements and questions that we can send different standards organizations and standards working groups specific questions around kind of, hey, this is what we're doing as 3GPP-SA3 or as 3GPP. We'd like to utilize this protocol, or we think you need to make a change to this protocol, and make very formal requests from that perspective. But there is a sense of respecting what the different standards organizations are doing and where their expertise is, and the understanding that all these groups need to be working together in kind of a collaborative way. I'm not sure if you wanted to add anything else, any of the other members of the panel.
Yeah, so I can say a few words about, coexistence. I think you brought it up, Rebecca, about coexistence in the unlicensed bands. So it's mainly 3GPP and IEEE 802.11 who are developing the cellular and the Wi-Fi standards respectively. And I know they've had joint workshops. They do talk about their needs. Personally, I think it could be a better job. But I think, for example, if you see what ETSI came up with recently, in 6 gigahertz, for example, they've come up with a common sensing threshold, which did not exist in the 5 gigahertz band. So I think the standard groups are learning, and they're understanding that more and more systems have to coexist. I definitely think that it could be better. But at the end of the day, industry has partitioned itself into standard bodies, and they've developed standards specific to a certain system, and they have to talk to each other to better coexist. FCC, at least, unlike some regulatory bodies, takes a hands-off approach. We try to make the rules fairly broad, and we leave the details about specifications and standards and how systems should interoperate up to industry. And I personally think that has worked pretty well, and hopefully that will continue.
Thank you. Let me follow up with another sort of standards related question, and that is, Jeffrey, you had mentioned that it's hard for someone to barge into a 3GPP meeting and push a specific solution to a problem because it needs to be informed at both a technical level and make sense within the system that they're working with. So can academics, small businesses, entrepreneurs, do they have an opportunity or means to be able to participate in those standards organizations?
Yeah, that's a good question. Participation is definitely a combination of kind of being in the room, being present, having a voice, having an opinion on multiple different topics, as well as providing informed contributions, building kind of that reputation for an organization. So that's kind of what makes it hard for like a newcomer to come in and say, here's a solution to this problem that might be way out from left field. It doesn't quite make sense. It'll be looked upon with more skepticism because that person might not kind of have that presence in the group or have that technical expertise of the system. But it is a good point of, yes, academics, small businesses, really many organizations can participate in specifically 3GPP Their working procedures are you have to participate through a membership which you purchase from your regional SDO. So from the US perspective, we are a member of ADIS, and we purchase a 3GPP membership from ADIS, and we attend on behalf of ADIS. It is a cost. It's not a small dollar amount. It's definitely an investment to be in the room and making those contributions and having a voice.
Jeff. Going to go back to an audience question here, and this one is detailed, but we've got 4 likes on it, so hopefully it'll. So this one, I guess, is for Professors Reed and Tripathi. Can you provide a little more detail on the difference between polar coding and convolutional coding?
Yeah, okay, so basically what we have in LTE for low rate channel, like control channel, physical downlink control channel, we have convolutional coding. But in 5G, we moved away from that and started using polar coding. Now, the way to look at these two is this. In convolutional coding, we have a formula, a mathematical formula that performs XOR functions of the current bit and certain number of previous bits. Okay, and we get the code symbols, convolutional code symbols. On the other hand, this polar coding is a kind of block code. So we have a block of bits that go into the polar coding, and we get a block of symbols out. And those symbols that are coming out, they are obtained by doing some kind of transformation, something called channel combining, channel splitting. Okay, but basically polar coding is a block code. And the reason that we are using this polar coding in 5G is that compared to the convolutional code, this kind of polar code is more efficient. So it can be obtained reliably, plus it consumes less power. So you get better performance at a lower power consumption. So that is why we moved from convolutional to polar in 5G. Thank you.
That one. Thank you. Next question is, I think this may be about, well, close to the last of the audience questions, and then I'm going to ask some closing questions for the panelists. But there's a question for, I believe, Dr. El-Moghazi, because it says there's been some concerns about the security, especially of the cybersecurity and threats. Is there a plan for the ITU to incorporate the zero trust architecture?
Thank you, Rebecca. I was motivated by the title of the conference to dig more into what the ITU is doing with security and the standardization sector. The ITUT is doing a lot of things when it comes to security. In fact, it has a dedicated study group for security issues. However, I haven't found the zero trust architecture adopted in there, and again, nothing related to the security on the spectrum level. So maybe in the ITU we are talking about different language. Remember, it's 193 countries, so perhaps it's still too early for a concept like zero trust to be adopted at the international level. Thank you, Rebecca.
Thank you. I think we've got about 10 minutes left, and I'd like to kind of open it up to the panel and ask each one of you if you can talk a little bit about what you see, I guess, or perceive or envision for 6G.
I can go first. My view of 6G, I think there's two key things. One is that it'll fix problems with 5G, as most standards tried to do, fix the issues with previous standards. I think they'll probably try to improve the latency and some of the power issues associated with 5G. And number two is the inclusion of AI everywhere throughout the network. And although this is being done today to some extent, and there's a lot of research going on within academic circles, it's going to take a standardization process to get the full benefit of AI. It's going to be tough, but I think it's going to be an important contribution of 6G.
Yeah, I would like to add, so as Dr. Reed mentioned, latency would be probably around 100 microseconds. Today in 5G, it is below 1 millisecond. The peak data rate would also be very high, right? So from 20 gigabits per second, we plan to go to 1 terabits per second. Right? So it's like 1000 gigabits per second. So it will be very high. What technologies do we use? So as Dr. Ghosh mentioned, if you need high data rate, you need to go to higher band. So the FCC has done something called some Spectrum Horizons order. So they have released some spectrum for experimental licensing at this moment. Okay, it's more than 100 gigahertz kind of a spectrum we are looking at. So we will see some terahertz communications and we would need new kinds of antenna technologies and power amplifier technologies because Dr. Reed mentioned the power efficiency is a big problem. You can lose 50% of the power just within 1 inch. Okay, within 1 inch, you will lose 50% of the power in the power amplifier. So you have certain power amplifier rating. By the time it goes out of the antenna, you lost 50%. So efficiency will be a problem. So we need to do something to make it work. Yeah, thank you.
So if I may add to those thoughts from Jeff and Nishith, I think, well, there is this feeling in the industry that the even Gs are more successful than the odd Gs. 4G was more successful than 3G. So as Jeff Reed mentioned, that maybe 6G will fix all the problems of 5G. But just seriously, 5G is attempting to sort of do many things in one standard. And the expectation is that not all of it will be completely come to fruition in the 5G rollout. So if you look at Spectrum, 6G, definitely there is a very strong active research community and effort in the, I won't necessarily call it terahertz, but in the high hundreds of gigahertz range. But when you go up there, your architectures change completely. And it will be interesting to see what, how you make a mobile cellular network work when your propagation limits you to maybe a few meters. And another thing I want to mention, which we didn't talk about much in this panel, is about both the core network as well as the virtualization, the Open RAN movement, where now you're talking about really having remote radio front ends, and then everything is done. You're basically disaggregating the entire radio access network. Yes, that will happen in 5G and will get started in 5G, but I think making it standardized, right now you have a lot of bodies working on this, but it's not a standard in the sense of how 3GPP has standardized the radio interface. Doing that will really open up what you can do with things like AI, for example, because now you have a lot more control points into the network. You have a lot more ability to get data from different parts of the RAN. Today, the RAN is a very closed system where unless even the operators sometimes have a hard time getting into the internals of this RAN. Again, a lot of these ideas will be fleshed out in 5G, but maybe they get actually standardized and deployed in larger scale in 6G.
Yeah, but I would like to add one point that we are looking at the tip of the iceberg right now. 5G has a lot of potential. Okay, so by the time we go to 6G, we will see many more things in 5G.
Rebecca, if I may add, and taking advantage of the hat of the developing countries, given that perhaps I'm the only one in the African continent right now that will talk about the 6G. So my question is that, do we really need the 6G things? Are we already utilizing the 5G? Not talking about some countries that have not yet deployed 4G. And a second question inspired by Professor William Webb, is one of the participants. Why are we still playing the generation game? Why it's 5G or 6G? At least in the 5G, this is a unilateral world. Everybody is talking about the 3GPP. For me, and this is my personal view, it's not a good thing. We need some sort of competition. We need countries like the US investing in having new technologies for the radio access. Otherwise, I don't expect 6G to be much different from 5G is currently designed to be. And if you look at the draft white papers of 6G, it's enhanced version of 5G. So perhaps it's time just to relax and think about what we really need for the future. And thank you all. Thank you.
Yeah, and I'm happy to go last, hoping you can still hear me. I think from a security perspective, as it was with 5G, the security architecture, we're going to continue to evolve and, first of all, fix things we didn't quite get to with 5G. And secondly, we're going to have to address all the security issues that researchers find as the 5G implementations become more and more mature. But just like what happened with LTE, it was a technology that was around for 10 years. Researchers continually find issues with the standard, with the implementation, with the deployments. So from a security perspective, I think the security posture will continue to evolve and become better and better over time. I think that is very relevant for 6G. And I think from a kind of functionality and feature perspective, I think with 6G, there's the opportunity to actually realize like the cloud native design principles that went into 5G that we might see realized, but we might not, as was mentioned. I think there'll be the opportunity to actually deliver on some of the promises 5G brought, but we didn't quite get to. And I see some of those cloud native principles making their way to the RAN. So that antenna really just becoming a physical piece of hardware where everything behind it is virtualized, kind of like an internet application.
Thank you for bringing us back to the radio access network also. So we've reached the end of our allotted time for the tutorial panel, and I would like to sincerely thank all of you on the panel for your generosity in sharing your knowledge and your time with all of us. So virtual applause for all of you. We will now go into a break, but before we go, let me just say that the agenda for the day will be visible on the Blue Jeans events platform during the break. ISART 2020 will resume at 1 o'clock with opening remarks from Dr. Cheryl Jenko, the Director of ITS, and that will be followed by our key leader roundtable discussion. Joining NTIA's Doug Kinkoff from our ISART co-host, we will have Walt Copan from NIST and Terry Fries from the University of Colorado Boulder, who will then set the stage for the remainder of ISART. And then we will follow this afternoon then with Dr. Joe Evans, who will close out the formal presentations for today with a keynote address. The afternoon panelists will all be available to chat with you in breakout rooms after the conclusion of the Q&A following Dr. Evans's keynote. Information on accessing those breakout rooms is in the confirmation email that you all received and in the ISART app for those that are able to download and access it. And technical support will be standing by as this is our very first fully virtual ISART. So thank you all for joining us this morning from the tutorial. We'll see you this afternoon and good day for now.